All right, so let's talk about the general second order circuit. Okay, so this is the general second order circuit is when you have a system that is neither solely series RLC or solely parallel RLC. It's just any configuration. And you, at this point, then have to derive the differential equation that describes that because the roots, it's going to have some characteristic equation. It's a second order circuit, so that it's going to be a second order quadratic, a quadratic formula in terms of S. And it'll have different characteristic roots. So you can't go and use just the standard alpha and beta values we've been using for the series and RLC or series and parallel RLC circuits. You have to start from basic principles and derive them. Okay. Here's the general procedure on how to do that. So everything is going to fit into this standard, whatever the transient response is, plus the steady state response. That's the total response. So, just realize before we even go into this, let's just remind ourselves that the x of t is going to be some x at infinity plus x transient of t, and that's what you need to find, right? That's what you're going to go and look for. So this is the steady state piece, x at infinity, and then there's the transient piece. Okay, so to find the transient response, x transient of t, just remove all the sources and then follow these steps. Apply KVL, KCL, etc. It could be nodal or mesh if you needed to do that. You could do voltage divider, current divider, whatever was going to get you the right thing. And you're going to get your second order ordinary differential equation. You're then going to solve the characteristic equation and get the roots S1 and S2. And the system then is going to fall into one of these categories, which we've kind of looked at already. It's either going to be S1 is, so if S1 is not equal to S2, and they're both real, then you have an overdamped response. And the x transient of t, and I should probably be writing on these transients here because let's just keep the notation really clear. This is, you're only finding the transient response in these, right? So x transient of t is going to be that a1 e to the s1 t plus a2 e to the s2 t. So it has the same form. Poles of the system, as sometimes they're referred to, or another way to say it is the roots of the characteristic equation, S1 and S2, are not going to be, you can't find them by the same alpha and beta values that we were using before. Okay. All right, so another possibility is that it's underdamped. And in this case, S1 and S2 are complex, where you have that S1 and 2 are equal to negative alpha plus or minus j omega. Now, this alpha value is different than the alpha values that you found in series and parallel RLC circuits. All right, and when you find it that way, or you're looking for the transient response x of t, it's going to be in some form e to the minus alpha t times a1 cosine omega t plus a2 sine omega t. Oh, sorry. Yeah, I'm sorry. That's right. It's plus a2 sine omega t. All right, and then the last possibility is that it's critically damped, and we know that happens when S1 is equal to S2. And you have then that the transient response x of t, as we've seen before, is a1 e to the s1t plus a2 t e to the s2t. So it's really similar to that overdamped response, except the second variable the second term has a t product in there. or a T variable in there. All right. To find the steady state value, you're going to look at the steady state conditions. The inductors go to short circuit, capacitors go to open circuit. Your total x of t then is x steady state plus x transient, as we discussed. All right, and then you're going to find the initial conditions from those no jump conditions. All right, so let's then take a look at an example problem. So here we have a circuit that's got a 12-volt source in it. It's got a couple of resistors and an inductor and a capacitor, and the resistive, inductive, capacitive network is wired in such a way that after the switch closes, right? After that switch closes at t equals 0, it's wired in such a way that it's neither a series RLC circuit or a parallel RLC circuit. It's some other just arbitrary configuration. All right, we've been asked to find the voltage across the capacitor as a function of time, right, for t is greater than 0, and the current through the inductor, I of t, for t is greater than 0. So let's look at the transient response. And as we talked about on the last slide, to find the transient response, you turn off all the sources and then apply KVL and KCL. So we're going to call this point, well, it's already been labeled for us as point A, right? Point A there. So we're going to do a KCL at A, in other words, nodal. And we're going to do the nodal approach here. Okay, so we get, what do we have? We have I coming into the node, the current I flowing into node A. Okay, so we get an I. We have an IC flowing out of node A, so we get a minus IC. And then we get a plus 0 minus V over 2 is all equal to 0. All right. We'll remember that IC is this term here. That's going to be a negative C dV dt, right? So what we get is that I of t, or I, is equal to V over 2 plus 1/2 dV dt. And that 1/2 is the capacitance, is C. All right, so that's equation 1. All right. If we were to find the voltage, by the way, V of t, notice that whenever we do find it, equation 1 gives us a formula to find the current through the inductor right there, right? So so that we'll use that fact later. All right, let's take a look at another equation. Let's do KVL. We're going to do KVL going counterclockwise, okay? So that as we go around the loop, we get a plus 4I, we get a plus VL. As we're going through the inductor this way, we get a plus VL. And as we're going up through this 2 ohm resistor, we're definitely getting, here's a plus V across the resistor because it's in parallel with that cap. So we get a plus V, and that's all equal to 0. We know that VL is equal to L di dt. So if we plug that in, we end up getting a 4I plus L di dt plus V is equal to 0. And that's our second equation. So we now have a second equation that we can relate to, that's relating the voltage and the current. And so what we can do then is take equation 1 and plug it into equation 2. Everywhere that we see an I in equation 2, we're going to plug all of equation 1 in. So, right, so we have like a 4, instead of 4I, like this, it's going to be a 4 times V over 2 plus 1/2 dV dt, plus an L times the derivative of this thing. Oh, sorry. You know what? I should have put, instead of L, you know that L is 1 Henry, right? So we're actually just going to put in a 1 right here, 1 times di dt. So it's one less variable for us to track around through this scenario. So we get plus a di dt, so it's ddt of, and then where that I is, we're going to plug in equation 1, v of 2 plus 1/2 dv dt. All right, plus v is all equal to 0. And now we've got an equation, we've got some work to do here, but at least everything's in terms of one variable, voltage in this case, right? All right, so we're tracking down a path where we're leading towards being able to solve for, in this case, voltage. So so then, 4 over 2 gives us a 2v, right? 4 over 2 again is a 2 dv dt. Plus, now we're going to get a ddt of v over 2, so we get 1/2 dv dt plus ddt of dv dt is going to give you the second derivative of it, right? So we're getting half of second derivative of voltage plus the voltage is all equal to 0. And now we're going to collect some terms and put everything in the standard form of the second order term, the highest order differential operator in the front. So we get our 1/2 times the second derivative plus, we're going to collect terms on dv dt. So we have a 2 and then a half, so that's 5/2 dv dt plus, looks like we have a 2v and a v, so we get a 3v there is all equal to 0. So let's say we go ahead and multiply this by 2 and clear out those 2's in the denominator. So we'll end up getting the second derivative plus 5 times the first derivative plus 6v is all equal to 0. And there is there's our differential equation that describes the system. All right, so starting on the next page, I'll just write it again so we have it clear in front of us. We're going to try again. So some function satisfies this differential equation. And so we're going to try, try v of t is equal to a e to the st, some exponential. So we have an s squared plus 5s plus 6 is equal to 0. Okay. Oh, by the way, all times a e to the st is equal to 0, right? That's our. We've basically rewritten the formula with these s multipliers as derivative operators. So just to make sure that it's clear, that second derivative dv dt would be, s times s a e to the st, right? Or an s squared, right? So we see that, every multiplication by s is equal to another derivative, a further derivative in time. And you know what? I'm sorry, I wrote this wrong. There should not be an equal 0 in there. I wrote that wrong. The equal 0 is out on the outside. Here's an a e to the st, and that all equals 0. So clearly, this polynomial in S has to equal 0 if this equation is to be true. So we say, okay, we set this equal to 0, and there's our characteristic equation. This is one of those nice ones that factors real cleanly into an s plus 2 and s plus 3. Those are the roots of the characteristic equation. Well, in fact, we'll solve for the roots of the characteristic equation right now, right? Then for this to be true, then s is either equal to -2 or -3. So we see then that S1 and 2 are not equal to each other and they're real, and so we have an overdamped scenario. So we get that the transient response, V transient, T, is then A1 e to the -2t, that's S1, plus A2 e to the -3t, -3 being S2. Okay, so there's our transient. Now we do need to find A1 and A2, and we'll get there in a second on the next page. Before we go there, let's just quickly, let's see, I should have written that this is sort of step 1, it's finding the transient response. Now we're going to do step 2 and find the steady state response. Okay, so the steady state response, let's just look at the circuit at t equals infinity. After a very long time, we've got the 4 ohm resistor here, and we've got the inductor there. We have this 2 ohm resistor there, the switch is closed, and then there's the capacitor here. Right? Okay, and this is plus V, and we want to find V at infinity, yeah? Well, we know that at steady state, the inductor and the capacitor are going to go to their steady state behavior. So the inductor shorts, all right, and the capacitor goes open, right? And so we get then, we get a current I flowing through there. Essentially, this reduces down to, I didn't write this 2 ohm resistor here, 2 ohms. This is just a voltage divider, right? Where we've got by VDE, we get that V at infinity is equal to that 12 volt source times the 2 ohms over the 2 plus 4 ohms, which is 4 volts. So V at infinity is 4 volts. All right. So we have the general transient response with the roots solved for at this point, the S values. We need to find the A1 and A2 values, which we'll do in a second. And we now have the steady state response. So we're very close to solving this, right? So now that we've seen that, we're step 3 here. We can write it in terms of like the total response is, as we've discussed, it's the V steady state plus V transient of t, which is equal to 4 plus A1 e to the S1t. Oh, actually, we have S1, right? It's A1 e to the minus 2t plus A2 e to the minus 3t. And notice that we did this before going to look for A1 and A2. And I want to point out that the reason for that is you have to put in this steady state value first. You got to know what the steady state is at t equals infinity, because that's going to affect the t equals 0 values, right? We're going to use those initial condition values. All right. Speaking of initial conditions, let's go ahead and find those. Let's find A1 and A2. And we're going to find these from the initial conditions. And this is from the no jump conditions. So what do we know about the no jump conditions? We know that IL of 0 plus is equal to IL of 0 minus. And we know that Vc of 0 plus is equal to Vc of 0 minus. All right, so then let's look at t equals 0 minus and find out what those conditions were, and that'll let us know what they were at 0 plus for the inductor and the capacitor respectively. So at t equals 0 minus, we've got the inductor, we've got the resistor, but that switch has been opened, or the switch is still open, and we've got the capacitor. Here's our 1 Henry inductor. This is a 4 ohm. This is a 2 ohm. And the capacitor is a 1/2 farad. Let's talk about the voltage across the capacitor. So here's V of 0 minus. So what is V of 0 minus, or Vc of 0 minus? Remember, this is just before the switch closes, and things have been left in whatever state they've been in for quite a long, long time. So that capacitor should be full. If it's full, it's got charge up on the top plates and negative charges on the bottom plates. It's definitely got a voltage across it if it's full. If it's full, how about this? Let's talk about this. What about IL of 0 minus? Remember, if things have been in the conditions they've been in for a while, this is short-circuited, right? And the capacitor should be open-circuited, right? So if the capacitor fills up completely and there's no current, well, is there anywhere for current to flow, actually, I guess is the question, if the capacitor is full? That's right, this is 0, right? Because it can't go through the 2 ohm, the switch is open. Everything's been left in this condition for a long time before the switch closes, so the capacitors reach steady state. Yes, voltage across the cap is 12 volts. It sure is, and that is Vc of 0 plus by the no jump condition. And we also discussed that IL of 0 minus, well, the inductor's shorted, but the capacitor is in an open circuit state, and so there's nowhere for current to flow. So there's 0 amps flowing through there, and that by the no jump condition is equal to IC of 0 plus. I'm sorry, IL of 0 plus. So we need V of 0 then, right? We need to know V of 0. Now, actually, no, we know V of 0. It's equal to 12 volts. We have that. We just found that. What about dV dt? dV dt at t equals 0 is equal to what? All right. Well, we know that dV dt at t equals 0 is equal to IC of 0 divided by C. We've used that relationship several times. And so we actually have IC of 0. No, we don't. Wait. Oh, yeah. No, we don't. We don't have IC of 0. We have IL of 0, right? We know that can't jump. That is not going to change. But we don't have IC of 0 yet. And this is an important point to pause and remember that the current through a capacitor can change instantly. It can pivot and just all of a sudden have a completely different value, or in other words, be discontinuous about a switching event. And so what we should do then is look at let's look at t equals 0 plus. All right, so we've got the 12 volt source, the 4 ohm resistor, the inductor, the 2 ohm resistor, and the capacitor. Okay, and so here's the 4, this is the 1 Henry, and here's the 1/2 farad cap. We don't know the current through the capacitor yet, but we do know that the current through the inductor, IL of 0 plus, we already know that. That's 0. That's 0 amps. Maybe it's better to write it like down here. IL of 0 plus is 0. We know that there's some voltage across this capacitor. VC of 0 plus. Remember, that can't change, and that's that 12 volts that we already found. So that inductor is not going to let any current flow through it, which means then that all of the current is going to flow down through this 2 ohm resistor. So what we end up finding is that IC of 0 is equal to 12 volts, the voltage across that resistor, because that's in parallel with the cap, right? Divided by its 2 ohms, or it's 6 amps. Okay, so let's make sure we draw IC, right? IC is always shown as flowing, from higher potential to lower potential, right? So it's pointing into the positive terminal on the capacitor. And so the current is actually the opposite direction of that, right? So it's actually negative 12 volts over 2 ohms. The current is flowing in the other direction from that, so we get a minus 6 amps. All right, so then we can go and find this dV/dt. Then dV/dt at t equals 0 is IC of 0 over C. We found IC of 0. That's minus 6 amps. Divided by C is 1/2 of a farad. And so we get that it's minus 12 volts per second. Again, I think it's important to pause here. You end up doing these moves and solving series or parallel RLC circuits, right? And finding all these initial conditions. We have to do it for this general second order system as well. But I do want to pause here and point out that there's lots of little steps and small moves. Each one of these moves isn't super complicated on its own. Not like you're doing a whole giant nodal circuit or things like that. The capacitors, behave as shorts, or inductors behave as open, capacitors as opens, inductors as shorts, and you're kind of just finding these small little parameters there, and you're using those facts that the inductors and the capacitors get stuck in whatever state they're in between the switching events, and that turns this RLC circuit, whatever it is, into a much easier to solve thing. You don't even end up doing mesh and nodal, you're just kind of by inspection figuring out where things go, and paying attention to the nitty-gritty details of like directionality. All right, and so we finally found we have the initial conditions we need. We have V of 0 is 12 volts. We have dV/dt at t equals 0 is negative 12 volts per second. So we're ready to then go and find V of 0 and these items here. So we're ready to find A1 and A2 rather. So V of 0, if we put that in, is 4 plus A1 e to the s, t. When t is 0, you just get the A1, right? The anything raised to the 0 is just that thing. So, or is just 1. So we get a 4 plus A1 plus A2 is equal to, well, V of 0, as we found on the last slide, is 12 volts. So we get our 12 volts here. So what does that give us? That gives us that A1 plus A2 is equal to 8 volts. This is our equation 1 for in terms of finding the equations to find A1 and A2. And then we know that, remember that V of t is equal to 4 plus A1 e to the minus 2t plus A2 e to the minus 3t. And so if we look at dV dt, that's equal to, we get on the chain rule, we get a minus 2 shows up in front. And again, on chain rule, we get a minus 3 shows up in front. Okay, so there's the derivative itself. And now we can plug in for dV dt at t equals 0 is equal to, we get a minus 2A1, a minus 3A2, and all of that is equal to negative 12. And this is our second equation. What I would recommend is then putting those into a matrix. I mean, it's a pretty simple system. You could solve it without this too, but you get your equation 1 is A1 plus A2 is equal to 8, and then equation 2 is a minus 2A1 minus 3A2 is equal to negative 12. And if you solve this for A1 and A2, you get that A1 is negative 4 and A2 is 12. So we've finally arrived at the solution for V of t. Again, it's that V steady state, V at infinity, that was at 4 volts we found, plus the transient voltage, which we now know is, oh, I'm sorry, I wrote these backwards, my bad. A1 is actually 12, sorry about that, and A2 is negative 4. Okay, so we get 4 plus A1 is 12 e to the minus 2t plus A2 is a negative 4, so actually I'm going to erase that plus. We're going to have a minus 4 e to the minus 3t, and that's all in volts. And there's the solution to the first part of the problem. It's been asked to find V of t. But you'll recall that I think we said at the beginning of this lesson that once we found V of t by one of our first equations, in fact, our very first equation, the KCL at node A, I is equal to whatever the V of t, it's I is equal to 1/2 V plus 1/2 the derivative of V. So we can actually plug, now that we have the solution for V of t, we can plug into equation 1 on that KCL. We have that I is equal to V over 2 plus 1/2 dV dt. And so we'll plug it in. We have that I is equal to, so half of V, right? So we're going to divide all the terms, constants and coefficients, by 2. So the 4 over 2 gets us 2. 12 over 2 gets us a plus 6 e to the minus 2t, plus minus 4 over 2 gets us a minus 2 e to the minus 3t. And then we're going to add 1/2 of the derivative of that. So let's go ahead and put the half out front, just to keep our wits about us here. And now we're going to look at the derivative of V of t. The 4 goes away, that's a constant. And so we get the minus 2 comes out in front of the 12 for a total of a negative 24 e to the minus 2t. And then the minus, and we're doing the derivative of the negative 4e to the minus 3t term. The negative 3 comes out to the front. Negative 3 times negative 4 gets you a plus 12 e to the minus 3t. And now we factor those terms in here a little bit. So we get that we're going to kind of combine and collect terms. So we get a 2 plus, we have a plus 6 right here. And then we've got a minus 24, half of minus 24, right? So that's negative 12. So this ends up being a total of minus 6 e to the minus 2t. And then for the second term, we had a plus 6, right? 12 over 2 plus 6, and a minus 2. So it looks like we end up with a net plus 4 e to the minus 3t. This is the total I of t. Okay? That you'll notice that has the steady state value in it, right? 2. It has the steady state value of 2, so we know that I steady state is equal to I at infinity, which is equal to 2 amps. And if we wanted I of 0, well, you could just solve for it in this term. So it's you'd get a 2 minus 6 plus 4, right? So 2 minus 6 plus 4, if you just plug in 0 into all those t terms, and that's, 2 plus 4 is 6, minus the other 6, you get 0. Well, that wraps up our lesson on second order, general second order systems. And again, the steps are that the system is going to have a response that's something of steady state value plus the transient response. You find that transient response first, remove all the sources, apply your KVL, KCL circuit techniques, solve the characteristic equation, look at the kind of roots that you have, choose what kind of system response you're dealing with. You'll then find the steady state value, express the function as steady state plus the transient, and then you can look for those initial conditions.